since we just discussed computing arc length for parametric curves, we absolutely must also cover computing the surface of areas of revolution for such curves, because that is essentially based on this formula for the arc length. So let's cover that. Area of the surface of revolution for parametric curves. Right, so let's recall what was the situation with regular curves. We had, say we had a curve that was rotated about the, for example, x-axis, like so, and the curve looked something like this. Right, then what we would have to do to compute area of the surface of revolution resulting from this, we would integrate something that looked like 2 pi times the radius to the surface of revolution, this guy here, times ds, where ds is the element of arc length. Now, it will be absolutely natural to do this in terms of parametric curves, because basically we know how to express every term in here in the parametric case. So we know what ds is. We have already learned that ds, the element of our arc length, is what we integrated to evaluate arc length of a parametric curve, right? So it's this expression over here. So this is what we would integrate to find the arc length of a parametric curve. And then we will need to determine what r is, and that is really simple. So say, for example, we are rotating around the x-axis as we do in this picture. So what we would do is we would write s equals integral, say from a to b, and then we'd have 2 pi times the radius of the rotation, and in this case radius of a point here in the graph is its y-coordinate. We would just put y-coordinate over here like so, and then we'd have the expression for ds, and that would be it. So this here is I guess it's not a and b but alpha and beta, because these were the range for t, and yeah, dy over dt squared integrated with respect to t. So this here is the area of the surface of revolution when you rotate about the y-axis, and when you have to do the same for the y-axis, then the radius of such a rotation, so then you're at a point somewhere here, and you're, say you rotate it like so, and then your radius is this distance here, which is the x-coordinate of your point. And so all we have to do is to take this same formula and replace y of t with x of t in it. And so let's see, so this is the rotation about about x-axis, and we get this formula here. And for the rotation about y-axis, we have that s equals integral from alpha to beta 2 pi times x of t times the same expression for the arc length, for the element of arc length. And this is it. So all we had to do was to recall the formula we used for a regular curve and to express each component of it through the quantities involved in a parametric curve. So this is here the area of the surface of revolution. For the curve x equals x of t and y equals y of t with t between alpha and beta. To give an illustration, let us compute another example. Let's look at another example. 3, let's say. So compute the surface area for the sphere of radius r. Okay, so the way to obtain the sphere of radius r is to rotate a circle of radius r. So we need to start with a circle. And let's see. Looks a bit... okay, so this is more round circle. And so we'll take this circle of radius r. So the way to write it in parametric form would be to take the unit circle. Okay, so this is the parametric equation for the unit circle, right, with t between 0 and 2 pi. This is something that we discussed when we looked at the unit circle. And since it has to have radius r, we will rescale both x and y by the constant r. So this is the equation, parametric equation of the circle of radius r. And then what we'll do is we'll rotate it about the x-axis, for example. And in fact, we don't need to rotate the entire circle. We can just rotate its upper half. So we'll just rotate the part from 0 to pi. So the part that corresponds to the angles from 0 to pi. So that would be this part over here. So we take angles from 0 to pi and rotate them about the x-axis. Rotate that part of the curve about the x-axis. And since we know what is the area of such a surface of revolution, it's the integral from 0 to pi, and then we have to put 2 pi times y of t, because this is rotation about the x-axis, so we have to put in there the radius, the distance to the x-axis, times the square root of dx over dt squared plus dy over dt squared dt. And so this gives us the following. We have the integral 0 to pi, and 2 pi over here, times sine, let's see, this is not, this is r times sine of t, multiplied with the square root here, which gives us, let's see, dx over dt is the derivative of this expression here, which is minus r sine t squared plus r cosine t squared, everything with respect to dt. And so this becomes, after simplification, let's see, this becomes r times sine t times, in here we can simplify these two terms. So what these two terms give us is r squared sine squared t plus r squared cosine squared t. And so together they amount precisely to r squared. And that is r squared under the radical. We take the square root, we get simply r. So this is the expression we have to integrate all in all. And it's equal to 2 pi r squared integral from 0 to pi of sine of t dt. So it's a very simple integral here. And we get 2 pi times r squared times minus cosine t from 0 to pi, which results in 2 pi times r squared times minus 1 minus, and then I have to subtract minus cosine at 0, so that is minus 1 again. And this gives me 4 pi r squared, which, if you recall, is precisely the area of a sphere of radius r. So if you ever looked into this, this would be precisely the formula for the area of a sphere of radius r. And so indeed we have successfully computed the correct expression. So what we had to do was just to take the equation for the parametric curve and basically plug it into the same formula we used for a regular curve, except that we here need to express every quantity, so the radius of revolution and the element of arc length, in terms of the quantities involved in the parametric curve. And that gave us the correct answer right here.